In today's session, we're going to be looking at building upon our knowledge of abstract data types, and we're going to use linked lists to create a new type of structure which is known as binary trees. A binary tree is a very useful data structure. It's actually quite simple. If you understood linked lists, this is going to be a breeze for you. So let's begin by looking at what binary trees actually are. The tree is a general data structure that describes the relationships between data items or nodes. And if you remember nodes basically consist of a data item and a pointer. In the case of a binary tree, the parent node of a binary tree has only two child nodes, hence the binary nature of it. It is an abstract data type which is implemented through other abstract data types. So for example, linked lists are quite commonly used to create binary trees. But we need a special version of a linked list, one that not just has a single pointer, but actually two pointers, the left pointer and the right pointer. And we'll look at that in a moment. But before that, let's look at a visual representation of a binary tree. A binary tree structure normally begins with the root node. Think of it as an upside down tree. Trees have roots at the bottom and leaves at the top. With a binary tree structure, we have the root node at the top and the leaf nodes at the bottom. So start with the root node. It has two pointers, left and right, and eventually items are ordered based on whether they're less than the root node or greater than the root. If they're greater than the root node, they go towards the right, and if they're less than the root node, they go towards the left. Now from the root node, you can draw two substructures like the left subtree and the right subtree. And that makes it very easy for us to traverse or go through a tree type structure which can become quite complex. Eventually you'll reach a node which doesn't have any other nodes attached to it, and that's known as the leaf node. The rules that operate on a binary tree type structure are as follows. The left node always contains values that come before the root node. The right node always contains values that come after the root node. For numbers, this means that the left subtree contains numbers less than the root node, and the right subtree contains numbers greater than the root node. And for words, as might be the case in a sorted dictionary, the order is alphabetical. So the left tree contains characters which are less than the root node, and the right subtree will contain a combination of characters which might be greater than the root node. So the root node basically is your pivot. Based on that, you can compare what's on the left subtree and the right subtree. Now, binary trees are not just useful for ordering of data, they're also useful for evaluating expressions. Now on screen you can see a binary tree which can evaluate the expression a plus b times brackets c minus a. So the left subtree has the a plus b expression, the right subtree has the c minus a expression, and the results of both of these expressions are multiplied together. So if you think back to reverse Polish notation and perhaps in order expression evaluation, all of those are possible via binary trees as well. Binary trees, just like linked lists, have three main methods or actions, and they are inserting a node, deleting a node, and traversing a particular binary tree, or perhaps what you might want to call it, finding or searching the value of a particular node. As such, the algorithms for these methods are pretty straightforward. So let's start by setting up a binary tree. If the tree is empty, then the next item is entered at the root node and we stop. If the current node equals the root, then we are going to repeat steps 4 and 5 until the current node is equivalent to null. That means you've reached the end of the binary tree. So what are we repeating? Well, if a new data item is less than the value at the current node, we go left, else we go right. We then set the value of the current node to whatever node it's reached, or we set it to null if there are no nodes after that particular one. We create this new node, we enter the data, and we repeat steps 4 and 5 all over again if there's another value in the list. What happens if you want to insert a new value into your existing tree? Well, let's look at a binary tree insertion task, and then we'll work our way towards the relevant pseudocode. We've got a sequence of numbers which are to be formed into a binary tree, and these numbers are on screen. Hopefully you understand how a binary tree works. So your first task is to form a sorted binary tree diagram, and this can be done step by step. So if you look at the sequence 20, 17, 29, 22, 45, 9 and 19, the first value to be entered is 20. Now since the tree doesn't exist, 20 becomes the root node. So do pause the video and try to create a sorted binary tree diagram using what you've learned so far. And when you're ready, continue. Okay, you should have arrived to a solution which looks something like what you see on screen. So check your solution, and if it matches, well done. If it doesn't, perhaps you might want to revisit how you went around ordering the nodes. Now this process of creating this binary tree structure on paper should give you an indication of how the pseudocode would work. So in this particular case, we're creating a type, a record type called node, and we're declaring the item as integer. This will hold the value, for example, 20. And then we're declaring two pointers, the left pointer and the right pointer. And these are also going to be integers because they're going to be pointing to various indexes, position 1, position 2, and so forth. So you've got this structure which has 3 data items, and using this record type, we can now create an array called myTree, which is going to have values of node type. So each of these indexes will have these positions: item, left pointer, and right pointer. We're then going to declare a root pointer, which is going to be the starting point, and the next free pointer, which is going to point to the next free space in that array. What you're in essence creating is a structure like this in memory. So you've got myTree, which has 9 values, 0 to 8. Items can be stored in there, and the left and the right pointers point to the items either on the left-hand side of the root node or the right-hand side of the node. So in this particular case, our root is 27. The left pointer points to index 1, which has 19, and of course 19 is less than 27. On the right-hand side of 27, though, we go to index 2, which is value 36, and that's greater than 27. If you look at now index 2, the left pointer doesn't point to anything, it's -1, so that's null. That means there is no value stored to the left of 36. But to the right of 36, the value is now placed as index position 3. So you go and check that value. Even though binary trees look like circular nodes or rectangular nodes, whichever way you think about them, in essence, in the computer's memory, they're basically a table that has one column dedicated to the data values and the other 2 columns dedicated to the left and right pointer. And these left and right pointers are related to the index of the item that is stored. So you could really create a binary tree using 3 one-dimensional arrays. That's possible as well. So how do we go about searching this particular tree structure? So it's okay to set it all up in memory, but how do we go about finding items in there? The pseudocode involves the use of a function and pointers once again. We set up our root pointers. Chances are you've already declared it in the previous pseudocode, and we're going to be utilizing that. The item search is what we want to find, and the item pointer is the value that keeps being updated depending on whether we go left or right. Null pointer is set to -1, and we set the root pointer to 0 because that's the index location where our root is stored when we first insert it into the structure. So the function find will import this value to look for. For example, you might have 8 values in there and one of them is 19 stored somewhere in index 7, and you want to find that. So find this particular item search, which is our parameter, and we're returning an integer saying either we found it, which returns an integer of the index where it's located, or -1 if we can't find it and it's reached the end of the structure. So the item pointer is set to the root pointer because we begin with index 0, and while the item stored at the current item pointer is not equal to what we're looking for, and the item pointer is not the null pointer, basically you haven't reached the end of the list and you haven't found the item, keep doing this, which is comparing whether the item at the current pointer is greater than the item search. If that's the case, we make the pointer stored in the left pointer as the item pointer, or we make the pointer stored in the right pointer column as the item pointer, and we loop again. And this loop is going to carry on by comparing, okay, let's just say if you're finding the item 16, is 16 greater than 27? In our case, that isn't true because 16 is of course lower than 27. Therefore, we're going to change the item pointer to the pointer stored in the left pointer column for the item 27. So in this case, the left pointer column contains 1, so the item pointer becomes 1. We then go back to the loop and check the item at index position 1. Is that item equal to 16? No, it's not. And we move to the if condition. Is 16 greater than 19? Well, that's not true either. Therefore, the item pointer now becomes the left pointer for item 19, which is 4, and we loop once again. Is the item in index location 4 16? Well, that's it. It is 16. Therefore, the item pointer's item is equal to item search. So the while loop is fulfilled, and we exit the loop and we return the item pointer, which is now 4. If you want to have a go, try to find item number 42 in the tree. Trace it out using those headings at the bottom right hand corner, and you'll probably find that the root pointer and the item search won't change, but the item pointer will change as you go through every iteration. One of the best ways to work out how an algorithm actually operates is to use a trace table, create the headings for the variables or the conditions that are applicable in the loops or the selections, and then you can work out the values step by step. That will give you a greater understanding of the algorithm. Talking about algorithms, on screen you see the binary tree search algorithm. If tree is empty, report error and stop. Otherwise, set the current node to the root node and repeat the following steps until the program is stopped. If the required data item is equal to the value at the current node, then report found and stop. If required data item is less than the value at the current node, then go left, else go right. If no node is found, then report error or item not found and stop. So insertion, on the other hand, works something like this. What if we want to insert a new value? So currently index 9 is the next free pointer. Yes, it's got an item in there, but that's irrelevant because it might be something which has a number that's been set by default or stored previously when we wanted to delete something. So the next free pointer is at index location 9, root pointer is at 0, and we want to now insert the value 72. We're going to insert the value at the next free pointer. So in index position 9, 72 gets in there. And now we're going to compare this with the item at index location 0, which is the root pointer, and then we're going to check whether it's greater than or less than, and according to that we're going to update the pointer. So 27, well 72 is quite clearly greater than that, so we go to right pointer 2. We check index location 2, 36, it's greater, we go to the next one. So the right pointer now is 3, so we check index position 3, which is 42. Well, 72 is still greater than that, so we go to index position 5, which is in the right pointer. We check index position 5 is 89, 72 now is less than 89, so we check the left pointer for that index, which is 8, then we jump to 8, 8 is 55, 72 is greater than 55. We check the right pointer of index position 8, that's -1. We change that to 9 because that's where 72 is, and then the left and right pointers for index position 9 are set to -1 because there's nothing to the left or right of 72 yet. Now that's how a binary tree insertion will work, and we're going to look at the pseudocode for it. Now in this particular case, what we've decided to do is to extend our type node, and we've got the item, the left and the right pointer. We're also going to have an old pointer and a left branch per se, which is a boolean, so you know whether you're going to the left or right. There are multiple ways to do this. You can choose it to do it this way, or you can choose any other way possible. Again, the initialization part is fine. You've got your array of 12 items of node. We declare the root pointer, the next free pointer, the item pointer, the item we want to insert into this binary tree, and an item add pointer, which will be the pointer where we're going to add things in. There's a null pointer which is set to -1. Now remember, you can reuse some pointers, you can use arithmetic, you can do it any other way possible. This is just one possible implementation of the pseudocode. There are multiple out there. You might want to create your own variant as well. So once we've got that set up, the procedure to add or insert a node to the binary tree goes as follows. We're going to use the item add as a parameter, and first we're going to check if the next free pointer is equal to the null pointer, because if it is, then there are no free nodes because you reach the end of our list per se, or our binary tree. Therefore we're going to output no nodes are free. Otherwise, we're going to start by making sure that the item add pointer is the same as the next free pointer, and the next free pointer is now going to change to my tree's next free pointer, dot left pointer, which probably will be -1 at that point in time. The item pointer is going to be set to the root pointer, and we're then going to check the item pointer whether that's equal to the null pointer, because that indicates that the tree is an empty tree. We then set the item add pointer as the root pointer, because obviously there's nothing there, so we're going to use that first location. But if it hits there, if something else is there, then we want to find out where to insert this new leaf node. And we go through the same type of routine. While the item pointer is not the null pointer, that means you're not at the end of the list, keep doing this. The item pointer becomes an old pointer. We store that value there. Then we check the item at the current location, make sure that if that's greater than what we're trying to add, then we choose the relevant branch. So in this case, we choose the left branch, we set the boolean to true, and we update the item pointer to the left pointer. If that's not the case, if the item is greater than whatever stored at the current item pointer, then we choose the right branch, and in that particular case we set the left branch boolean expression to false, and we update the item pointer to whatever's in the right hand column, so item pointer dot right pointer. We then exit the loop. We then use the flag to navigate left or right and update pointers accordingly. And once we've done that, we got to the right place, we then store the item to be added in the new node. In this particular case, we're simply going to say, well, my tree item add pointer, whatever pointer you ended up, dot left pointer is null, right pointer is null, because the last item, the leaf node, will have both left and right pointers as -1. Then the item is inserted at that particular pointer. Now, of course, there are multiple ways to go around this pseudocode, but one of the best ways to do that is to use a structure like this and follow the algorithm to check whether you can insert 18 in the right place and update the pointers accordingly. So quite clearly 18 has to be added in position 9, but how would the algorithm work? So trace it out. You could use the following headings: left branch, next free pointer, item add pointer, root pointer, item adder, item pointer, and old pointer, all the various pointer variables. The next free pointer is already set to 9 because that's the next free pointer. Item add pointer becomes 9, root pointer is already set to 0, the item we want to add is 18. Now follow the insertion pseudocode and check whether the pseudocode actually works. Pause the video and go through the process. Hopefully you got something like this, so do check your work, and if you got it, fantastic. If you didn't, then you might want to go back and double check whether you haven't missed a step or two. If you were using this structure, this is how the answer should look like. Okay, that's enough about insertion. Let's move on to deletion. Not only can we work in numbers, we can also work with letters, and letters can also be put in ascending or descending order. Now, in this particular case, we've got a binary tree of names, and quite clearly Joe is greater than Freddy, but we want to delete Joe. Now, what do you think will happen when Joe gets deleted? What would the new structure look like? Have a think about it. Well, hopefully you picked up either Gelly would come up or Sean would come up. So if Joe is deleted, there is no way of knowing which direction to take at that particular node to find the details of the data that's beneath it. Now, in order to do that, there are two possible solutions. One solution is to store Joe's subtree in a temporary storage area. We take it out and then we rewrite it back to the tree after Joe is deleted. The effect is that one member of the subtree will take over from Joe as the root of the subtree, and you decide what that is, whether you want Gally to come up or whether you want Sean to come up. That's the programmer's decision. Solution 2 is to mark data Joe as deleted so that the data no longer exists, but it can maintain its action as an index for that part of the tree, so the subtree can be correctly negotiated. So when we're outputting the data, we ignore Joe because that's deleted, and we move on with the relevant indexes depending on the traversal of the algorithm. Alternatively, you could just put a null or none or -2 or some other value in the item part for Joe, which indicates that do not output this particular one. All you would need is an extra selection where you're saying that if something dot item equals -2 or null or none, then do not output it basically. Again, this depends on how you want your structure to work. One requires a bit of extra coding, but you will have much more accurate binary tree. The other one is just we're storing extra values that we're never going to be using. So as the binary tree becomes bigger, you end up with more deletions. It's probably better to go with solution 1. The final part that we're going to look at before we go into the coding side of things is binary tree traversals. This is a quite common exam question. What are the three ways to travel a binary tree structure? They are basically in order, which is left, root, right, pre-order, which is root, left, right, and post-order, which is left, right, and root. Now, if you look at the nodes, don't consider the nodes to be the data. These are not items 1, 2, 3, 4, 5, because that's not the right binary tree structure. 2 should be on the right hand side of 1, for example. So these are just nodes. Okay? So based on these nodes, we could travel using in-order traversal, which basically means that the root is in the middle. Pre-order means the root is on the left-hand side. Post-order means the root always comes on the right-hand side. Now, based on that, the way you traverse a binary tree, you could end up with a different set of outputs. So in-order traversal, where the root is in the middle, so A plus B, left, root, right, that's in order. That's the way we are used to things. Now, if we do that, we start with the left node, which in this case is node 4, and the root node for node 4 is node 2, so that comes up next, and the right node is node 5. Now, that means we've taken care of the left branch. We now look at that branch as a whole. The root for that branch is 1, so node 1 comes up next, and the right-hand side for that is node 3. Now, if we use pre-order traversal, which basically means the root is pre the normal conventional order, so instead of being in the middle, it's on the left-hand side, we start with looking at what's the left branch and the right branch. The left branch is 2, 4, and 5, so that's left. Right is 3, so we start with the root, which is node 1. Then we have to move to the left-hand side, so we go to the left subtree. Now in here, what's the root? That's 2, so node 2 comes second. Then we go left, that's 4, then we go right, which is node 5. Once we've exhausted all the left side, we then go towards the right side, and now there's only one node there, which is node 3. Now if we traverse using post order, post means at the end, so therefore the operator, in other words, moves towards the end, which is kind of like reverse Polish notation, if you remember that. A plus B in RPN becomes AB plus, left, right, root. So post order is very useful when we want to use a binary tree structure with a compiler to evaluate RPN expressions. So in this particular case, we're going to start with left. The leftmost node is 4. Then we go to the right, which is node 5, and then we go to node 2, which is the root, because now you've just dealt with the left branch. Some people get confused here and they say, well, if you go left and that's 4, why don't you jump to 3? Well, we're not using the middle one as the pivot. We're first looking at the entire left branch. And if you go all the way to the left, node 4 is to the left, and the root for node 4 is 2. Therefore, the right-hand side of node 2 is 5. So it will be 4, 5, and 2. And then we go back to the right-hand side, and there's only node 3. And finally, we've got the root, which is node 1. So depending on the traversal algorithm you use, you're going to have a different set of outputs. So for RPN, we're going to use post order. If you're going to evaluate normal expressions, in order might be the case, and so on. Now your task is to implement a binary tree structure using Python. Now you might be wondering what happened to the deletion pseudocode. Well, we'll get to that because there's a lot of different approaches. I would like you to try to work out the pseudocode for that. Of course, I'm going to give you some Python code in a moment. I'm not going to explain that Python code, but you will have access to that in this video, and a link to a REPL with the code in the description of this video. As with all things computer science, it's all too easy for people to just copy the code and then cram it. To avoid that type of situation, the binary tree I'm going to share with you will give you a menu system, and it will allow you to insert nodes manually. So for example, if you set 20 as the root, you can then insert 30 to the right of 20 and 15 to the left of 20. And the reason I've done that is because I want you to build on this code so you can try to create an automatic insertion mechanism where when you type in the root node, any node after that can automatically be slotted either to the left-hand side or the right-hand side. You might need to combine the two insert mechanisms in the methods along with the search mechanism and try to create a new version of the code. Play around with this code, and generate a better algorithm than the one that I'm giving you. On screen, you see a bit of code that allows you to create a node using a class method in Python. This is the most effective way to code a binary tree. Of course, you can use a record type, you can use a generic definition, you can even use 3 arrays to do it, but all of that will take you a lot longer in exam conditions. So get into the habit of just using classes and instances of those classes to create these. So this class will have a lot of different methods, and the first one is setRoute, which defines the route. The next method allows you to search for data, and that's pretty straightforward. The next few methods allow you to do in-order traversal, post-order traversal, and pre-order traversal. Again, these are pretty straightforward. It's just the order of output, really. So we just want to print out the data item and then update the pointers accordingly and then reprint it. So you're just using recursion here. This particular routine allows you to insert to the left branch. And similarly, this particular routine allows you to insert a node into the right branch. So it's these two routines that might need to be combined to make an automatic insertion method. And finally, this is the main part of the program where you have a menu system that allows you to insert, search, or output various traversal algorithms. Just make sure that you spell things correctly. Of course, you can enhance this one as well. Now remember, the link to the actual code will be available in the description. That brings us to the end of this particular lesson. Hopefully you know how a binary tree structure works and how it is implemented. You should be able to explain the 3 binary tree traversal algorithms: in order, pre-order, and post-order. And of course, for paper 4, you should be able to code this in the allowed programming languages, for example, Python. The best thing to do with binary trees and linked lists is to try coding them, try to understand how different methods work. And once you get a hang of these, you're not really going to forget it. That's all from me for today. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.